Hey everybody, in this video we are going to talk about something called a colligative property. A colligative property is a property of solutions that depends on the concentration of particles of the solute instead of the identity of the solute. So it doesn't matter what type of thing that you are dissolving, it only depends on the number or the concentration of particles. Now, before we continue, let's talk about this concept called a Van Hoff factor, which is abbreviated as the letter I. This factor tells us the number of particles a solute can split into. Most molecular compounds, including sugars, proteins, I2, and etc., do not split apart when they dissolve, so they have an I value of 1, since basically there's only one particle. Now, something like sodium chloride, NaCl, splits into Na plus and Cl minus upon dissolving in solution. So since one particle or one formula unit of NaCl can form two ions, then that means that NaCl has an I value of 2 since each NaCl can form two ions. Now, this is where things get a little bit complicated, but we can do this. A weak electrolyte, and if you remember, a weak electrolyte is simply a weak base or a weak acid, and there could be more, but these are the two that we are going to focus on. So weak electrolytes actually do not split completely when dissolved in water. So for example, HF, hydrofluoric acid, is a weak acid because it is not on the strong acids list that we memorized a few dozens of videos ago. So, since HF, or hydrofluoric acid, is a weak acid, it will partially ionize into F- and H+. Therefore, we are guaranteed to have at least one particle per HF, since HF itself is a particle. But since HF can sometimes split into two, but not always, then the overall I value will be greater than 1, but less than 2. So now let's take a look at a very special acid. H2SO4, or sulfuric acid, is a strong acid, and that means that it can become H plus and HSO4 minus. So it can definitely turn into two ions. But HSO4 minus is a weak acid since it's not on the list of strong acids, so it will partially ionize into H plus and SO42 minus. When we consider acids, we have to consider the H's popping off one after the other instead of everything coming off at once. So the first time it pops off an H+, it will be essentially 100% complete since it's a strong acid. But the second time around, it's not really complete. And because of that, you could have at least two particles, the H and HSO4, but the second time around where you make HSO4 turn into two other particles, now that's not guaranteed, and because of that, you can have between 2 particles, which are guaranteed, and 3 particles, which is not guaranteed. So, because of this, the I value of H2SO4 will be greater than 2, but less than 3. Now, before we continue, let's talk about how you can tell if something is a sugar or not. Now, if they tell you it's a sugar, then you know it's a sugar, of course. But what if they gave you the name? Well, there are some neat tricks. So for sugars, anything that ends with an ose, such as glucose, sucrose, dextrose, xylose, or even lactose, and this list goes on, anything that ends with an ose is typically a sugar. Now, what about proteins? Well, typically, but not always, proteins end with ase. So amylase, hexokinase. But, pepsin is an exception, and that's fine because we just have to know that pepsin is a protein. And of course, the list goes on and on and on. So, I guess these are just good tricks for you to figure out whether something is a protein or a sugar or if it's not, just in case you're in that situation. Now, we talked about the I value, where the I value is the amount of particles that something can split into. But can the I value deviate, which means that can the I value be lower than usual? Can particles split less often than we predict? Well, of course. So, one thing that could impact our Van Hoff factor is the charges, especially for ions. If the charges get higher, which means that there's more attraction because Coulomb's law, then this can actually cause ion pairs to form in an ionic atmosphere. And what that means is that ions are attracted to other ions in solution rather than to the water. Normally, we expect ions to be attracted to the water and be surrounded by ion dipole forces like that. And this would be Na+, for example, and these would be the partially negative ends. But sometimes in solution, especially when the charges are high enough, ion pairs can form in solution where something like Na+ and Cl- can be bonded ionically in a way even though it's dissolved in solution. So in other words, it's as if it never dissolved in the first place. So this causes the cation and anion not to separate as we expected because, for example, NaCl can form ion pairs in solution. And because of this, since it's not splitting into two particles like we expected, then the I value will be lower than what we predicted for NaCl. So if NaCl starts forming ion pairs, then the I value will be less than 2. Now, a great example of this is something like AlCl3. We know that Al is a +3 charge and the Cl's are -1. Now for high charges like these, the I value will deviate more because we expect the I value for AlCl3, which can split into Al3+, so that's one particle, and 3 Cl-, the other 3 particles, and we expect the I value to be 4. But that's not the case. Usually, it's around 3 because of these ion pairs that form, primarily due to the fact that Al3+ is highly charged in terms of magnitude, and because of that, it can cause ions to be attracted to one another in solution. So overall, your I value will be lower than usual depending on how charged your atoms are. Now, what other things can cause deviations for I? And these deviations are always going to decrease the I value. So dissolving more substance, or in other words, increasing the concentration of the solute, can actually make the I value lower than predicted because as the ions get crowded, now this applies to ions because if we look at substances that don't split into things, then none of these apply because these things that don't split into anything will always have an I value of 1, and that doesn't deviate. But for things with an I value higher than 1, things can start to change really fast. So for these things, the ions can get crowded, and because of that, they are more likely to form ion pairs with each other via ionic bonds, rather than form ion dipole forces with water molecules. This keeps some of the dissolved salt as a single particle, which is not what we anticipated, just like over here, and this actually lowers the I value as well. So let's look at some data to see if it's true. So this is molality, and as you decrease the concentration, you see that the I value gets closer and closer to the ideal I value of NaCl, which is 2. But as you can see, as you increase concentration and you go to the left side, you can see that the I value starts dropping. And over here at 1 molality, it is at 1.81, which means that for every particle of NaCl, it will split into, on average, 1.8 particles. And in this case, the particles are ions, so 1.81 particles of ions, which is a weird thing to think about, but you can think about it like this. For every 100 NaCls, you will get 181 ions that form. So you could think of it that way too. Now let's talk about some symbolism. So what does bracket NaCl mean? So if you put brackets around NaCl, what does that exactly mean? Well, that means that they want the concentration of NaCl typically and almost always in molarity. So if I put brackets around NaCl, I am talking about the concentration of NaCl, and I just made up a number and I said that the concentration of NaCl is equal to 5.0 molar. Now, let me ask you this. What is the concentration of Na plus or Cl minus? Well, they are also going to be 5.0 molar as well, because 5.0 molar of NaCl has 5.0 molar of Na plus, because for every 1 mole of NaCl, there's 1 mole of Na plus that forms from it. So if it's 5 molar of NaCl, which is the concentration, then that means that there must be the same concentration for the Na plus, since for every 1 mole of this, you have 1 mole of this. Now let's continue and see why we are talking about these things. So, for these colligative properties, you have to use the concentrations, and that's why it's called a colligative property, because it depends on the concentration. And we will see that there are a few formulas that we have to use, and these formulas involve concentration. So for these colligative properties, make sure to multiply the concentration of solute by the I value to get the concentration of particles. For example, if I had 2 moles of barium hydroxide, each barium hydroxide, and by the way, this is a salt, so it will, dissociate completely into its ions. So each BaOH2 will fully dissociate into Ba2 plus and 2OH minus, since it's a salt once again. So the I value is ideally 3, and we will use the ideal value unless told otherwise. Therefore, for every 1 mole of BaOH2, there are 3 moles of particles. And why is this? Well, for every 1 mole of BaOH2, there's 1 mole of Ba2 plus and 2 moles of OH minus. So, the concentration of particles is actually 2 molar times the number of particles that each BaOH can produce, which is 3, and you get that the concentration of particles is going to be 6 molar. So in general, the concentration of particles is equal to the concentration of the solute times the Van Hoff factor. Now, for colligative properties, there are other things that you also have to do. When you're trying to find the total moles of substance, you have to consider the fact that the solute can split apart into many moles of substance. So, for example, if I had 20.0 moles of water and 3.0 moles of dissolved sodium chloride in water, then how many total moles do I have? Well, you might say 23, but that's not correct, because in reality, there's actually 20 plus 2 times 3, since we have to remember the Van Hoff factor, and this is because for every 3 moles of NaCl, there are 3 moles of Na plus and 3 moles of Cl minus, and that already makes 6 moles of particles. So 6 plus the 20 moles of water, which don't change, will give us 26 moles in total. So keep a note of that when we're doing these colligative properties. Now, what if we wanted to find the mole fraction of water? The mole fraction of water is the moles of water over the total moles. And in this case, for the total moles, we have to consider that the sodium chloride can split into 2 particles. So that means that for every mole of NaCl, there are 2 moles of particles. So doing the mole fraction for water, we get 20.0 divided by 26.0, and it turns out that the X for water is going to be 0.769. Now you might be wondering, why am I showing you these things? Well, because we are going to do some colligative property calculations that involve these types of problems. So let's talk about our very first colligative property. It is known as Raoults Law, and this law states that dissolving stuff in a solvent, like water, makes it more difficult for the solvent to form vapors, since less solvent molecules occupy the surface of the liquid, which is the place where they evaporate and form vapors, when solute molecules are there as well. So, solute molecules and solvent molecules now make up the surface, which is where the solvent, or the ones in blue, are supposed to evaporate. And since these solute molecules take up that space as well, then it's harder to create vapors because there's not as many solvent molecules on the surface to evaporate. In addition, solute particles are attracted to solvent particles and form a very stable bond with them, which is why they dissolve in each other, because they are able to form this bond, such as an ion-dipole bond, which is fairly stable. Because of this, it actually takes more energy than normal to break these new, usually stronger, IMFs and allow the solvent to evaporate. Thus, dissolving stuff can decrease the vapor pressure of the solvent. So Raoult's law is actually an equation. It tells us that the vapor pressure of a solution is equal to the mole fraction for the solvent times the vapor pressure of the solvent if it was pure and without any solute dissolved in it. Now, the P can be anything as long as the units are the same on both sides. So you could have ATM, you could have torr, and etc. Now, we only look at the solvent because typically the solvent is a volatile one and the solute, such as a salt, is essentially non-volatile. So that's why in the equation, we only consider the vapor pressure caused by the solvent. And yeah. Now, what happens if we dissolve two or more volatile liquids together? So let me change that wording, together. Now, what happens if we have two or more volatile liquids together? Well, we have to consider the vapor pressures that each of them can give off. So the total vapor pressure that is exerted by the solution will be equal to the mole fraction of the first volatile substance times the vapor pressure of the first volatile substance if it was pure. And you have to add that to the mole fraction of the volatile substance number 2 times the vapor pressure of the volatile substance number 2 if it was pure. So all in all, this formula is telling us that when the mole fraction of the volatile substance, which is usually the solvent, is being lowered, then the vapor pressure of the solution will also be lowered in response. So let's do a question. Find the vapor pressure of water in a 1.264 molality solution of sodium hydroxide at 0 degrees Celsius if the vapor pressure of pure water is 4.6 millimeters of mercury at 0 degrees Celsius. So we have a bunch of information, and I'm going to dissect the things I need. So I'm going to dissect 1.264 lowercase m, because that stands for 1.264 moles of sodium hydroxide for every kilogram of water. So I have two valuable pieces of information that will help me solve this problem. We need to find the mole fraction somehow, and we have the moles of NaOH. And we technically have the moles of water since we have the kilograms of water. So we just need to convert the grams of water to moles of water, and we end up getting 55.49 moles of water. Now, to find the mole fraction of water, we simply take the moles of water and we divide it by the total moles, which is the moles of water plus 2 times the moles of NaOH, since one NaOH can produce 2 particles and the I value is 2. So you simply multiply 2 by the molality to get the moles of particles. And after setting up the expression for the mole fraction, you simply multiply it by the vapor pressure of pure water at 0 degrees Celsius, since that's what we're looking for. And it turns out to be 4.6 mmHg. And multiplying all this out, the mole fraction of water times the vapor pressure of water that is pure, you will end up getting 4.4 millimeters of mercury as your new vapor pressure for this 1.264 molality solution. So, using molality and the information we were provided, we were able to calculate the mole fraction and the new vapor pressure of the solution. So, that's cool, right? Well, let's move on to our second colligative property. This one is known as the boiling point elevation. So it's similar to the idea that the vapor pressure decreases upon adding solute. So it is harder for solvent molecules like water to boil with solutes because solutes that dissolve well typically form stronger bonds with the solvents, via ion dipoles between water and Na+, and this is of course stronger than the H bonds between water. And since they form stronger bonds with the solvents, then they are thus harder to break. Because of this, the boiling point increases when solutes are dissolved. So the equation for boiling point elevation is the change in the boiling point is equal to a constant Kb times the molality of the particles of solute. And for calculating the particles, don't forget the I. And let's now do a question based on this. At what temperature will water boil at 1 atm if 2 moles of glucose, which is a sugar because the OS, and it has an I value of 1 because of that, so what will happen if it is dissolved in 315 grams of water? The Kb for water is 0.512 degrees Celsius per molality. So we simply have to use the equation. So Tb is equal to K times the molality. Now, how did I find this molality? Well, I know that molality is moles of solute over kilograms of solvent. So it's 2 moles of glucose over 0.315 kilograms of water. And simplifying that, we get that there are 6.35 moles of glucose for every kilogram of water. And I underlined it here because the answer has to have 2 sig figs. So I plug the molality there. So 6.35 moles per kilogram of water is the same thing as 6.35 m. And multiplying this, the m's cancel out, and we're left with a boiling point change of 3.3 degrees Celsius. So, as a result, we know that the change in the boiling point is going to be 3.3 degrees Celsius, and we know that the boiling point increases. So this change in temperature must mean that it's increasing the normal boiling point at 1 atm. So we know that 1 atm in normal conditions, the boiling point of water is going to be 100.0 degrees Celsius. So to find the boiling point of the solution, we simply add 100 to 3.3, and we get that the new boiling point of the solution is about 103.3 degrees Celsius. Now let's talk about another colligative property, freezing point depression. Freezing point decreases with added solute because the solutes interfere with the bonding of solvent molecules during freezing. Solvent molecules need to form bonds with one another to freeze, and the solute-solvent interactions, which are mostly IMFs, make this harder since the solvent particles are bonded less to other solvent particles, as they also like to bond with the solute as well. Therefore, a lower temperature is needed to get these solvent particles moving slowly enough to form strong IMFs with other solvent particles, whilst the solutes interfere. Therefore, dissolving solutes lowers the freezing point. So the equation for freezing point depression is very similar to that of boiling point elevation. The change in the freezing point is equal to a constant Kf times the molality of the particles of solute. So don't forget your I value. Now Kf is different for every solvent, as Kb is also different for every solvent. So watch out for that. Now, as we know, the change in freezing point will result in a decrease in freezing point from the normal freezing point. So let's look at this question. It is the same exact question, but it's asking for the change in freezing point instead. So, at what temperature will water freeze at 1 atm, or normal conditions, if 2.0 moles of glucose is dissolved in 315 grams of water? The Kf for water is 1.86 degrees Celsius per molality. So, in the previous slide, we found that the molality of the solution was 6.35 with 2 sig figs. And therefore, you just simply do the math and multiply the constant by the molality of the particles. And we get that the change in freezing point is going to be 12 degrees Celsius. So since the normal freezing point of pure water at 1 atm is going to be 0.0 degrees Celsius, then the new freezing point is going to be 0 minus 12 degrees Celsius, since this is freezing point depression, which means that it's going to decrease. So our new freezing point is going to be negative 12 degrees Celsius. Now let's talk about our final colligative property, osmotic pressure. So before we read the explanation, let's see what happens in this tube. On one side, we have 1 molar sodium chloride as indicated by these red dots, and on the right side we have some pure water, and over here we have a semi-permeable membrane, which lets water through but does not let sodium chloride through. Now this system wants to reach equilibrium where both sides will have the same concentration of salt, since this side has too much salt and this side has no salt, and to reach a favorable equilibrium where the system is completely mixed, both sides want to ideally have the same concentration. So what can happen? Well, the pure water can flow through, as shown by this arrow, to the more concentrated side to dilute it, and by diluting the left side, we can get the concentration on the left as close to the concentration on the right as possible, which is 0. So what will happen is that there will be an osmotic pressure represented by pi, and this osmotic pressure will push the water to the left side, and on the right image you can see that the water has been pushed up, and as you can see, this pressure, this osmotic pressure pi, is holding up this much water, because normally what's supposed to happen is that both sides are supposed to be level, but since now this side has this much more water than this side, so this must mean that the extra water is being held up by the osmotic pressure, and the osmotic pressure pushes this extra water and holds this water up, since, as I said before, naturally, gravity wants both sides to be level. So, now let's read the explanation for what this is. The pressure needed to prevent the flow of water when water travels from a lower concentration to a higher concentration of a solute through a semi-permeable membrane is the osmotic pressure. Now, the process in which water travels from a lower concentration to a higher concentration of solute is called osmosis, hence osmotic pressure. You might have heard of osmosis in your biology class when learning about red blood cells, for example. Now, osmotic pressure could also be thought of as the pressure exerted by water when it undergoes osmosis, as shown in the images. Now, osmosis happens again because it wants to reach an equilibrium where the concentration of solids on both sides are the same. So that's why water travels from a less concentrated area to dilute the more concentrated area and try to make both sides the same concentration of particles. Now, how do we measure osmotic pressure? Well, once we get this happening where the water pushes the water up, we want to have a piston, and the piston will push down on the water that's leveled upwards, and it will push on it and make the water level again. And the pressure that this piston exerts to cause the water to be level once again is equal to the osmotic pressure, since they kind of cancel out and you're left with a leveled water. Since if the two pressures are equal, they will cancel out and there will be no net movement of water, hence why it is level. Now, this is just another representation of how osmotic pressure works and how it is measured, but it's a different apparatus, but the same concept. Now, the equation will be pi, osmotic pressure in atms, is equal to the molarity of the particles of solute times R, 0.0821, since we're dealing with pressure, and T and Kelvin. Let's try doing a problem. So, we need to find the molar mass of a protein in a solution of 0.021 grams of the protein in 25 mLs of the solution, and this solution turns out to have an osmotic pressure of 0.51 torr at 25 degrees Celsius. So how do scientists find osmotic pressure? Well, they set up this apparatus, and on one side they have pure water, and on the other side they have a solution. So, same deal, and we know that the eigenvalue of the protein is 1. We know that 0.51 torr is this much atm. We know that 25 degrees Celsius is 298 Kelvin, and we could find the molarity by knowing that it's going to be equal to the moles of particles over 0.0250 liters. And to solve for molar mass, I substituted the moles of particles for grams of protein over molar mass, and I substituted it into pi equals m times r times t. And doing the math, I get this as the molar mass. And remember, don't forget your I value, and thanks for watching. Have a wonderful day.